Great. All right. So our next speaker is Estelle Massart, who earned her doctorate in 2019 from Université Catholique de Louvain and is now a postdoc at the University of Oxford. She currently works on links between optimization and machine learning, but today she will be presenting work from her PhD, overview of a quotient geometry with simple geodesics for the manifold of fixed rank positive semi-definite matrices. I'm so sorry. Thank you.
Thank you. I just need to share my screen. Is it okay?
Yes, it's good.
Thank you. So thanks for the very kind introduction and for giving me the opportunity to present my work here. Indeed, this is work that I have done during my PhD under the supervision of Pierre-Antoine Absil and Julien Hendricks in UC Louvain in Belgium. So this work has a component in differential geometry, but I will try to hide it as much as I can, so that people with no background on manifold theory are also able to follow the talk. So let's first start with the story of this work. So during my PhD, my supervisor has been contacted by people working on wind field estimation and who are trying to design a good wind field model in order to be then able to design controllers for unmanned aerial vehicles. And so they have an area of interest like this one. Do you see the pointer or not? Well, I guess
yes, we can see it.
Thank you. And so they have an area of interest like this one, and they would like to get a model for a W, the wind field, at each point here of the area of interest. And so this W depends on the time, it depends on X, the location inside the area, and on some external meteorological conditions, such as, for example, the prevailing wind in the area of interest. So, of course, usually W will depend both on the prevailing wind orientation and magnitude, sorry. But here we will make the assumption that it only depends on the prevailing wind orientation that we will write theta I. And so for this talk, we just assume that theta I is varying, and extension to cases where the magnitude is also varying we have done that in another paper, but I will not present that here. So usually the wind field is also expected to be in 3D. So just here I have put a 2 here because the data that I have received are 2D. The methodology and all the presentation will not change if you just replace the 2 by a 3. We are just working here with data that were obtained in 2 dimensions. So the way they were modeling this wind field is by first discretizing the problem. And so they were placing a grid of n² points here on the area of interest. And then they were getting a big vector W bar by just stacking together all the values of W at different places at the different nodes. So here we have a W bar that just depends on theta I and on the time, and which is a huge vector, and which is assumed to be a Gaussian, multivariate Gaussian with given mean and covariance matrices. And so those mean and covariance matrices are also dependent on this prevailing wind orientation. And so the main difficulty with this approach was that each time they changed theta I, they needed to recompute those two parameters here. And this is very, very heavy on a computational level. So they needed to recompute those guys just to run computational fluids dynamics models, and who were very heavy to run. So they were trying to interpolate those values, so pre-compute a grid of known parameters values, so a grid of mu and a grid of covariance matrices for different values of theta, and then recover intermediary values of the mean and covariance matrices for intermediary values of theta by just interpolation of those grid of points. And so for the mean, it's not difficult because the mean is just, it doesn't have any specific properties, so we can just use any Euclidean algorithm, interpolation algorithm in the Euclidean setting. But for the covariance matrices, it's a bit more complicated, as we know that those are positive semi-definite. From their data, I can also say that they are very low rank, and they wanted to keep this structure through the interpolation process. So what we suggested them to do was to work on manifolds. So essentially a manifold, I will not go in a detailed explanation, but you can just think about it as a set that locally looks flat. So for example, a classical example is the sphere. So if it's a set that you can map locally through a set of bijections that have to satisfy some conditions and to some open set of the Euclidean space. So just think about a manifold as a set that locally looks flat. For this talk, at least it's enough. And so classical examples are the set, the Euclidean space, the sphere, and also several matrix sets, such as the manifold of fixed rank positive semi-definite matrices that we will use here in this talk. And the reason to work with a manifold is that if you just take the classical interpolation algorithm, what those algorithms will do is, at least for most of them, they will just assume that the matrix that you are targeting is just obtained by linear interpolation by just a linear combination of the data matrices for some weights that will depend on this theta. And so, for example, for Lagrange interpolation, you will have those weights. And the thing is that if you don't ask those weights to be positive, you might lose positive semi-definiteness. And even if you require those weights to be positive, you might see, it has been shown for several applications before this work and also in this work, that interpolation directly on the manifold works better and is usually more accurate than interpolation in the Euclidean space. And so that's why we have used interpolation algorithm that were designed on manifolds. We have just derived the theory required to get the tools on our specific manifold of interest. We plug them into those algorithms, and those are the results that we got. So essentially, this is the interpolation error on the training data, and this is like very, very surprising results. One of our training points was not interpolated at all by the algorithm, while all the others were very well interpolated. Where this comes from. So I will first explain you, speak a bit about the structure of the manifold, its geometry, and then I will go back at the end of the talk to the interpolation problem. So here we're working with S plus Pn, the definite matrices of rank P, and we will identify it to this quotient manifold. So for those of you who know that who know a bit about differential geometry and tools on manifolds, they might know that usually a manifold can have several representations, and each of those representations will give us a different notion of distance, of shortest path, and many tools will become different depending on the representation that you have chosen from the beginning. Here we are using that representation. And this representation comes from the fact that any PSD matrix A can be written like this. So for any PSD matrix A that has rank P, you can factorize it as Y transpose, where Y is just an N times P, so tall and skinny matrix with full column rank. So I will use this notation, R N times P star for the set of the possible Y matrices. And of course, this decomposition is not unique. This factorization, sorry, is not unique. And so you can just plug here any Q transpose, where Q is a P times P orthogonal matrix, and get the same left-hand side. So essentially, any PSD matrix A can be identified to a set of matrices inside this set. And all those matrices, you can just move along the set of equivalent matrices, so the equivalence class, using orthogonal matrices. So that's where this representation comes from. And so we have then taken a matrix, sorry. We have then taken a metric, and this gives us a notion of geodesics, so shortest path. So for the metric, we have just endowed the set R n times P here with the classical Euclidean metric. And then using the fact that the quotient map is a Riemannian submersion, but that's not important again. Here we got an expression for geodesics between 2 points. So essentially just the shortest path between 2 points on the manifold. And this is the key tool we require, that was required by our, the interpolation algorithm that we were wanting to use. So here's the results for the shortest curve. So essentially, if you have two covariance matrices here, C1 and C2, with corresponding factorization Y1 transpose and Y2 transpose, where the factors Y1 and Y2 are arbitrarily chosen inside the equivalence classes, then the shortest curve between C1 and C2 can be obtained like this. So just compute Y of t transpose, where Y of t is obtained as a linear combination between Y1 and Y2 Q transpose. And this Q here is just there to move Y2, the representative of the second equivalence class, as close as possible to the representative that was taken for the first equivalence class. So essentially we have here a proposed problem. And so Q is, the solution is well known. Q is the orthogonal factor of the polar decomposition of the product Y1 transpose Y2. And so that was a nice result. We were able to use it in our algorithm, but this result has a very strong implication, which is the fact that if this matrix is not invertible, then the polar decomposition is not unique, and we have non-unique minimizing geodesics. So on this manifold, if you have 2 points, you take two covariance matrices, well, you can have, under some condition, which is non-invertibility of this matrix, you can have several shortest paths between the 2 points. So it's like very counterintuitive fact when you are used to working on Euclidean spaces. But in the manifold theory, it's actually well known as a possible behavior, and this is strongly related to the notion of injectivity radius. So essentially, on a manifold, the injectivity radius is just the smallest distance between a point of your manifold and the points to which there exist several shortest paths from the initial point. So if you take as manifold the circle, you can see that the injectivity radius is just equal to pi. Because if you take some curves that are, some points that are at a distance that is smaller than pi, you have one clear way to reach the point in the shortest way. But if you take points that are antipodal, then you have two possible ways that are equivalent. So as a corollary, we have written this condition Y1 transpose Y2 invertible in a different way, and actually we can show that it's equivalent to having we can rewrite it in terms of the eigenvalues of the matrices. We can turn this condition into a condition on the eigenvalue of the initial matrix. And so we can show that for our manifold, the injectivity radius at a given point C is, so this is something I should have said, but here the injectivity radius does not depend on when we are, because there is kind of symmetry. So it's starting from that point or from that point, you will always have the antipodal point as the point that is the closest and for which you have two shortest ways. So injectivity radius is equal to pi everywhere for this, this manifold. But in our case, it depends on the location on the manifold, and it's equal to the square root of the p largest eigenvalue of our covariance matrix. And an immediate consequence of that is that if this injectivity radius goes to 0, you can have, so the injectivity radius will go to 0 if the matrix goes to kind of the boundary of the manifold. So if the P largest eigenvalue goes to 0, so if you are working on the manifold of matrices which are of rank P, but actually the matrix where you are has rank which is more like P minus 1, and the P largest one is almost equal to 0. In that case, the injectivity rate just goes to 0 as well. And so for points that are infinitely close away, so even points that are very, very close away, you can have several shortest paths between the two. And that's what was given us some trouble in our numerics. So now I will go back to the interpolation problem and explain a bit in detail how the interpolation algorithm that I have used was working, or is working, sorry. So the interpolation algorithm that I have used here has been developed by one of my colleagues, another PhD student in Belgium, who did all his PhD on the development of curve fitting algorithm on generic manifolds. And so he had some code that is available on his website. So if you are interested, you should have a look. And the way this code is working, or at least for the one that I have used, is that we will try to find a curve gamma among a set of admissible curves that will minimize this criterion. So the first term here is a regularizer, sorry. And the second one is a data attachment term. So essentially the first term will give us curve that is not very peaky, but like regular. And the second one will require the curve to interpolate at time ti. So just take t equal to theta if you want to match with the beginning of the talk, and the covariance matrices ci. And those two terms are balanced by a parameter lambda. And so if you take lambda going to infinity, you will enforce here interpolation. So you will have an interpolating curve. While if you take smaller values of lambda, then you will have just a fitting curve, but that will in general not interpolate your data. And that will be more regular. So the way these methods, these curves are represented is by Bézier curve. So those curves are parameterized by a set of control points that will give us the shape of the curve. And then the control points are optimized in order to satisfy this criterion. And here for the version of the codes that I was using, we don't solve exactly the optimization problem. But we compute some approximate solutions. So essentially, if you want to optimize directly the control point, it's a bit tricky. So what Pierre-Yves was doing at that stage of his research was just take some the optimality condition in the Euclidean setting and transfer the optimality condition to the manifold directly. So don't solve directly the optimization problem on the manifold, but he was solving it in the Euclidean space, getting optimality condition and transferring the optimality condition afterwards to the manifold. After that, he got some other versions, and he got recently a paper in which he was considering interpolation directly on the manifold, with the solving this problem, so directly on the manifold. So as I just said, for Bézier type curve, those are parameterized by a set of control points. So we have two subsets of control points, so the P and the B minus and B plus. So essentially the goal of the control points B will be to give us some information on the slope of the curve at the points like the training data, and the P are the value of the curve at the different training data. So in the interpolation case, we expect PI to be equal to DI. And so all the points that are in blue here on the picture, so this is, like, for this picture, it's in the Euclidean setting, but you should imagine the same picture on a manifold, so on a sphere, for example. And all those blue points, they were directly computed based on the optimality conditions. And then the the red points were computed in order to enforce the smoothness constraint. And so we have, by just evaluating numerically what was happening here, which I could see that those points were correct based on the wind field data that I was using. But the red point, we had some trouble. And the toolbox, like the code of Pierre-Yves, was working very well for different applications, so it was clearly not in depth. And it was really the geometry of our manifold that was causing some issues. And to explain this, I took another example for another manifold. This is just for illustration to explain you why we got some very weird interpolation error at the beginning of the talk. So we can actually also represent that on the sphere and see the same kind of behavior. So we computed the vector bi minus and bi plus, or at least the tangent vector, and then the way we were getting those points, control points pi that was wrong in our case, was by just taking the midpoint between, so just mapping the tangent vector here to the manifold associated to the two neighbor control points on the manifold, and then take the midpoint of the curves between the two. And that's supposed to be our pi. That's how the method is working, and that's for fitting case. In the interpolation case, pi is equal, should be ideally equal to the I. What we got in our case was a situation like that. So we were computed here the tangent vector associated to bi minus, and bi plus. Then we were mapping those vectors on the manifold. And then, well, if you take the midpoint between the two, we have here vectors that are too big, so that actually we don't get the point that we were expecting to get. So in some sense, we have kind of crossed this the cut locus, so the set of points for which we had minimizing geodesics. If we had a smaller vector here, we would have got minimizing geodesics. But then if you take two big vectors, you end up with a problematic situation like this one. And the point that our algorithm is providing us is this point, which is obviously very different to the data point that we were hoping to get. And so a simple remedy for that is just to reduce P, because since the injectivity radius is equal to the P largest eigenvalue of the matrix, if you just reduce P, you will have a larger eigenvalue and then a larger injectivity radius and less risk to be in trouble. So I have to say that in our data, the length of the vectors here that we were taking was always, even for the case where we got no trouble with a smaller p, much higher than the injectivity radius. So we were not able to directly enforce the condition, but we got like an improvement. And so a way to avoid those problems by just running interpolation algorithm on that manifold is to check whether the results that we obtain by taking a smaller p are kind of consistent or not. So here we see that just reducing p, we get some much lower error. And so it was obviously an error that was due to the fact that we were crossing cut locus and this issue with injectivity radius. While, so this is just a sanity check that I think should be done when dealing with that manifold, since this injectivity radius business and the property of the manifold can sometimes be a bit difficult. So to be sure, if you have at some point to interpolate on that manifold, I think it's a good idea to just try with smaller estimation of the rank, check whether the results are consistent or not. And if it's keep consistent but just a bit less accurate, it makes sense. But if you have some a strong decrease on the error at just 1 point, it might be that before that you were crossing this cut locus and getting into trouble based on the injectivity radius guarantee that was not satisfied. Okay, so I will now conclude. So this talk was about the manifold of fixed rank positive semi-definite matrices, and I went very quickly through it, through some results of, on the geometry of that manifold. So I should say that this manifold has been now like a lot studied. So there are several papers that address its geometry. So classical tools are well known, such as projection on horizontal and vertical spaces. Also the exponential map, the logarithm map. So those two aim to compute geodesics. But also more recently, we got expression for the injectivity ridges and the curvature of the manifolds. So here are some pointers in the case when you are interested. And implementation are also provided in the ManOpt toolbox, a generic purpose toolbox for optimization on manifolds. And if you are interested in more specifically interpolation on manifolds, so generic interpolation on manifolds for arbitrary manifolds, then you should also have a look to those three papers, sorry. So the three of them are for busy type interpolation on manifolds, but you should also find there some pointers to works that are not related on basic curves. And the one that focuses really on injectivity reduced issues is the second one. So that's all for me. Thank you for your attention.
And thank you, Estelle, for the excellent talk. This was very interesting. Davide, do we have any questions?
No, we don't have any question from Zoom.
And Hussam on YouTube?
Neither on YouTube.
I'll ask a very soft question then. I'm kind of amazed that you were able to combine ideas from so many different fields for the single problem. Was this something that just came naturally, or were these different interests you had and you were looking for a way to combine them?
So for the wind field application, I have to say that I didn't really work on it. So it was really collaboration with some researchers from MIT, and they were getting the data and sending them to us. So I didn't really dig on that. And for the rest, there is actually an interesting field of research which really aims to combine manifold theory and matrices and numerical linear algebra. So there are more and more works now that really focus on matrix manifolds, not only manifolds, but matrix manifolds. And so then you can also have sometimes kind of simplification, because there are very abstract tools that are studied in differential geometry and that are already well known when you are working on matrix manifolds. So it's not, I would not say that it's really like amazing, but thank you for your attention, for your kind comments.
Yeah, I think it's, I mean, both Estelle and Stefano, you've both had very impressive talks with a lot of really important topics. And I just want to thank you both again for talking, and also everyone for your attention. We're a little over time, but I think that's okay for now. I have just a couple announcements, and then we will switch to gather for further discussion. So next week, okay, Estelle, maybe you could stop sharing your screen. I will just share our schedule. Okay. Here we go. I hope everyone can see this. So next week we are, we have two more speakers, Theo Mary and Pawan Goyal. Sorry, and yeah, so they both also received honorable mentions from the Householder Prize competition. So we're very excited to be able to feature their talks. And our sister organization, ENLA, will also be launching again this week on Wednesday. So there's talks there that you can go to. And I believe that is it. So we will now switch to Gather. You should have received information in the reminder email, and we've also posted the links in the chats for YouTube and Zoom. And yeah, so we will see you there soon. Just grab a drink and relax. Thank you.